recording? I don't think I did. Okay, now I did. Okay, so we're going to use the hidden. We're going to use the hidden parameter. We're going to use threshold and step max only loosely. This is when you have problems running your code. I'll talk to you about how you can adjust the threshold and the stepwise function so that you have an understanding of how to accelerate your neural network to come to a solution. You have to remember that it's going to try thousands of iterations to solve the problem that you've given it, which is based on that formula. So this is the function that we're going to use, and we'll see that in the code. So here's the example that we've got. The aim is to provide a set of predictions using neural network for classifying wine quality based on number of attributes. So I have here 14 attributes and 178 observations. I'm going to have another variable, which is going to be the class variable, which will go from 1 to 3. So these are all the factors associated with the data set, with each one, and it associates with a quality. What we want to do is we want our neural network to basically predict what the quality is from the given attributes. Very much like we were trying to do a decision tree to predict what the classification is. And if you take the 250 class, we would use ordinal regression to do the same thing. So the first step is to ensure that there are no missing records in the data set. If we do have missing observations, we have to, again, handle them because every input must be between a 0 and 1. We don't have a choice. So we're going to have to figure out what to do with it. So in the code, what I've done is I've written for you this small function that basically says, here, I'm looking to determine from my wine data set how many NAs are in each column. Now, it's a pretty long function here, but I'm going to explain it to you. I'm just getting my chalkboard, my little marker out. If you were to run this piece of code by itself, is NA X. What that does is that takes a vector. This is a single vector, and it basically tells you whether or not each observation is true or false. Okay, so if there's an NA, it will return a true. If it's not NA, it's false. So in other words, I've got 100 observations. I've got 50 NA. I've got, let's do 99 regulars and 1 NA. It will have 99 falses because it's not NA and 1 true. What the sum, oh, why do I keep losing my mouse pointer here? There we go. I have to do that all the time. So if I basically sum that up, which is what this outer piece does, it will give me a count. So in that case, it would have been a 1 because I had 1 NA. Now, this is basically what we call, it's an inner function. I'm creating a function which basically takes in one parameter, and what it's going to do is it's going to use that parameter in here. That's exactly what it does. So what function am I doing? That's what this apply function does. Apply basically says apply whatever is in this third parameter here, this third parameter, this function, using this data set, and it's going to do it for every single column in that data set. 2 basically stands for every column. If it was a 1, it would be every row. So let me repeat that one more time. Apply, I'm going to go in the reverse way, says you're going to basically run some function on this data set. We're going to use this column. We're going to use columns, okay? Not this column, but this parameter tells me that I'm going to use columns. A 2 would be for columns, a 1 would be for rows. What function am I going to apply? I'm going to apply this function, which I'm creating on the fly. This is an inner function that basically will take in one parameter. That parameter is going to be every single column in this data set. It's going to do it one at a time. And what it will do is it will look at every column, determine whether or not it has any NAs, count them up or sum them up, and give you the result. And that's why we see here the class field has no NAs, alcohol has no NAs, malic acid has no NAs, ash has no NAs, and so forth. Once we're done, we're going to actually do the same kind of thing. We're basically going to run apply on the wine data set, each column, but now I'm going to do my function. Instead of being this function that I created, I'm going to choose another function called min, max, normal. You could choose scale, because some of you have used scale before. So you can use scale if you want, or you can use my function, which was the min, max, normal. Put it down when I'm done. Okay. All right, any questions? Any questions on that? Okay, let me go to the next slide, but I think we're going to jump right into R. Okay, let's jump right into R. Stop share, share, R. So here is the data set. Here's the code, actually. So my first line I'm going to run is the min-max normalization, because I want to bring this in. Clear this out, bring this out. Okay. Neural net, these are the two packages. So if you don't have them, you need to load them. Okay, so you need those two packages. Now what we can do is we can actually read the CSV file directly from this data set. So what I'm going to do is I'm going to show you the data set very quickly. Bear with me one second. I'm trying to get there. Trying to pull up the wine data set here. Share screen, website. Okay, here's the data set. So you can see here that I have all of these attributes, okay? Alcohol, malic acid, and so forth. And what we're doing is we're pulling the data from that URL. That URL has the CSV, which is, where's my R? Where did it go? Here we go. Which is at this URL. So if you run this line of code, you should get, let's see, did it run? No, it didn't. Hold on a second. The certificate has expired, so I have to see why it's doing that. Downloaded. I think I got to change it to, yep, 1 second, hold on. I think their certificate expired. There you go. Just change this from HTTP to HTTP, from HTTPS to HTTP, and it will work. Their security certificate expired, so it won't download without intervention. Okay. Once we do this, and I run wine, I'm going to run it by itself. We notice that it is a tibble down here. You can see where it says a tibble. So we're going to need to convert that at some point to a data frame. So let's do that now. We're going to do wine equals as.data frame wine, because we want to convert this back to a data frame. And now it looks like a normal data frame, which is what I want. Okay. Now, this line of code here is going to rename the columns, because if we look at the columns, they're labeled X1, X2, X3, X4, X5, X6, all the way up to X14. So we're going to rename them. So I took those names from that uci.edu website, and I just put them in here so you have the names. So when we run 12, which is really 12 through 14, it will rename my columns. And you can see here that all of my columns are set up. Here are my classifications in terms of the quality, the 1, 2, and the 3. Okay, now before I continue, does anybody have any questions? That I have now loaded the data, and I'm so far so good with that. I'm going to ask you to put in the chat window if you are okay. I've got 18 people. I want to get at least 12. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. Almost at 12. 11. I need one more. That means 2/3 of you are paying attention. There we go, 12. All right, so I got my 12. All right, moving right along. So now what I'm going to do is I'm just going to keep some variables here. I'm going to calculate the number of inputs, which is basically the number of columns minus 1, and the number of outputs I just set as 1. I'm only doing this so that I can use the variables later instead of having to write the numbers down. Okay? So now let me obtain a summary. I'm going to run these lines of code. I'm going to obtain a summary, and here's my summary. Now, I could have done this and have shown that I have no NAs. All of the numbers seem okay. I now know that they run, say, alkalinity, which is probably supposed to be alkalinity, runs from 10 to 30. Ash goes from 1 to 3. So I know I cannot use this for a neural network yet, but I will soon. What we're going to do is we're going to run this function here so that I can apply onto the wine data set. By column, I want to know, is there any NAs? That's what I want to know. So we run this, and it tells me there are no NAs in any of the columns. So it's an easy way to find out if you have any NAs. You can use summary. You do not need to use this. But what I'm doing is giving you additional ways of running various pieces of code. Okay, so this is not necessary. You could run summary and you could get the same answer, but this apply function is actually pretty cool because you can apply a function onto a data set by column or by row, which is what we're going to do actually here. What we're going to do is, in this case, we're going to create a normalized data set. And the way we're going to do this is we're going to use that same apply function. We're going to apply on the wine data set by column the function min-max normal, which is the one that I set up for you. Now, one of the differences that you see here is I don't have any parameters in, but I did when I ran it up here. The reason is because this function is an inner function. I have to give it all the parameters that I'm passing in. The min-max normal, if you take a look at that code, takes in one parameter as well. It takes in only a single column, which is what you want for when you're applying by column to a data set a particular function. So when I run this and I look at the wine norm, it has now normalized every single variable. They're all between 0 and 1, which is what we want. And so once we've done that, we are now ready to use that data set for a classification. Okay? Everybody okay with that? If you again could just type in yes on the chat. 1, 2, 3, 4, 5, 6, 7, 8. I want to get 13 on this one. 9, 10, 11. 3 more. Uh-oh. 12. No, 11. 12. One more. Come on. 13. There we go. All right. Cool. That's my little participation for the day. All right. So let's take a look now. Let's go back to our PowerPoint. All right. Now what we got to do is we got to determine the number of hidden layers and the number of hidden nodes. Okay. So for this example, I could use 1 or 2 hidden layers. I can have a fairly simple neural network. I could use 2, a little bit more complex if I want. 3 would probably be overkill. Probably doesn't make sense to do 3 because you have such few observations and such few inputs. So we're going to either use 1 or 2. Now, when you run your neural network, I would suggest that you try and do both. You know, try it with 1 layer and try it with 2 layers just to see how the responses, how your predictions go. We're going to use the formula from the previous slide, which was the number of observations divided by some alpha times ni plus n0. So we're going to choose an arbitrary alpha as 2. And why am I choosing 2? Because I have a very smaller data set. If I had, 60,000, 80,000, 100,000, I could slightly increase this if I wanted to. or I'm sorry, if I had a larger number of either observations or variables, I might want to do that so I can kind of adjust the number of nodes that I'm going to get. Here, I'm going to choose the smallest number, which is 2. 178 divided by 2 times 14, and you will end up with approximately 636, and I get this number of 7. And that's not bad because we have 13 inputs, 1 output, which is going to be our 14. So 7 kind of sits right in between there, and I can put them into a tree-based item. Where did the 13 come from? So the 13 is the number of inputs. NI is the number of inputs. NO is the number of outputs. Does that make sense, Andy?
Why is the number of outputs here? I see your note at the bottom, but I don't quite understand why we're going with 1 over 3.
Okay, you actually could change it to a 3-node classification, but it's a 1-node classification because I got 1 variable.
Got it.
But I can split it into 3 nodes if I want to, in which case this would slightly change.
Is that 13 the
number of inputs, the number of variables?
So we have 14 in this data set.
One of them is your output.
Oh, okay. Got it.
Did that make sense? Everybody good? Okay, so right now we're going to basically have 1 output for now. Even though there are 3 possible classes, I'm going to push them into 1 output. Okay, I can push them to 3 outputs, but we're going to do the 1 output first. So now the formula for A and N in this example, we're basically going to create a formula, and that's what we're seeing here. Okay, this is my formula. There is no shortcut like in linear model. You can use the period and stuff like that. You cannot do that here. You've got to put the whole formula. Wow, I lost my mouse again. So we literally write out the whole thing. Still lost the mouse, which doesn't help. Okay. We write the whole formula, and then we're going to pass that formula into the neural net right here. We're going to pass in our data, and now I've got this hidden parameter. This hidden parameter is going to take a vector. If it's a single number, you could write hidden equals 7, because we had said 7 nodes. Erase that. I could have written 7. Sorry. I'll get used to this pen thing. Could have written 7. Okay, and I wouldn't have needed this at all because it would understand that it would all be in 1 layer. However, if I want multiple layers, I will have to pass it in as a vector. So here I pass it in as a vector 5, 2, with the first parameter being the number of nodes in the first layer, the second parameter being the number, or the second element in the vector being the number of nodes in the second layer. I'm going to pause right there. Does that make sense?
How did you determine that it should be 5 nodes in the first layer and 2 in the second layer?
Okay, so what I did was I split them up in almost like a 2/3 or 1/2 ratio. So if I had 7, right, I really wouldn't want, let's say I had 8, I wouldn't want 4, 4.
Okay, so you want the first one to be larger than
you want the first one to be larger, correct? Okay, now, again, that is in most situations, I would say a predominant number of situations, but there are specific situations in which the structure of the internal nodes is very, very different.
Okay. And sorry, one more.
Oh, no, go ahead.
Why did you go with 2 hidden layers on this one instead of 1? Like you said, you could have just done 7. Like, what is the logic to determine?
The logic is I would have had to have written this twice because it would have been 2 separate examples.
Okay.
Okay. There was no reason other than the fact that I want a little bit more complexity, right? So I can see how to show you how to do a 2-layer example.
Got it. Thank you.
But the biggest question I get from students is, well, how do I choose really the number of layers? That is really where you get into a full neural network class, right? To really understand the different types of neural networks and how you can do your feed forward and back propagation, and you can go forwards and backwards and do all these weird things to these nodes to try and get the number. The more complex your neural network is, the more likely you are to overfit your training model. In other words, it will work well for the training model, but it won't do so good for the test model. Does that make sense?
I have
Yeah.
a question.
Yep.
Where does that 5 nodes come from?
Which 5 nodes? The 5 from the first layer?
It says 5, comma 2. Where do the 5 nodes come from?
So how many nodes did I choose to have for my calculation before? 7, right?
7.
So now I have to split that 7 into one. If I want 1 layer, then it's just 7. If I want 2 layers, I have to split up the 7 nodes into 2 layers. Does that make sense?
No.
Okay, you got 7 nodes, right?
Yes.
I got to split them up into 2. Got 7 coins. You're going to split them up into 2. Give me
Okay.
some possible permutations. But if I split them up into 2, make the first group larger than the second group. What would your permutations be?
Heads, tails.
No. Just the coins. I could have 7 coins in the first group and no coins in the second group, right?
Oh, okay.
But that's a 1 layer solution because I have nothing in the second layer. I could have 6 nodes in 1 layer, 1 node in the other layer, right? But that's a problem too, because technically you really only have 6 nodes trying to produce 1 more node, which will then produce an output layer. Does that make sense?
Okay.
Okay. So I could try and
Yeah. I don't see where the 5 come from on the other slide.
Hold on. Let me get this. You've got 1, 2, 3, 4, 5, 6, 7, correct?
Mm-hmm.
I need to split them up. So I'm going to split them up into 2 layers. I just said I'm going to choose 2 layers. So the first layer, I have to put a certain number of nodes. So what I did was I chose 5 nodes, 1, 2, 3, 4, 5. So therefore, my second layer has to have 2.
Okay.
So therefore, I have a 5-2 set of hidden nodes.
Oh, okay.
That make sense?
Yes.
All right. Okay. Eraser. Okay. So when we then run our neural network with that information, it's going to create an object that we put into this variable called NN. You can call this whatever you want. You can call it NN1, MDL, you could call it neural1, it does not matter, okay? But you can, it's an object that you run. So now, let's go see what that looks like in R. I gotta find Zoom. Okay, you see my code? All right, so here, I'm going to run my neuron estimate. This is just a straight calculation. The only thing that you probably haven't seen is this ceiling command. If you run the number of rows divided by 2 times inputs, outputs, where did they come from? Well, remember up above, I have my inputs and outputs. That's why I did that up there, so I could just use this. The ceiling will basically round up. So if you just take this and run it, you get 6.35. So if I take the ceiling of that, it will basically round it up to 7, which is what I want. So my neuron estimate has the number 7. Now, if I take the total, note the difference between the column names and the names here, right? So if I take column names, that's my, why did I do this? I have 14. This N here is the number of column names. So just don't get confused here based on that lowercase n, please. Because technically the lowercase n in the PowerPoint refers to the number of observations, but I'm using n here for number of columns. I'm going to explain why in a second. It would really stink if all the time you see this down here. I could basically do FRM equals class by alcohol plus malic acid and so forth. That's a very long item there. However, the issue is this, is if you have 768 or 800 columns, that will take you a long time. So I've written a small function up here in R that will actually take all of the column names and create the function for you, create the formula for you. So I'm going to show you how this works. N here is now listed as the column names. So this is a vector of column names. And I'm going to ask you at each point that I do this, please, I'm going to ask you, does that make sense? Because otherwise this is going to be, if I go too far, you get lost. It's hard without going back to the center. So I want to make sure we're okay at every point in time. So could you just type yes in the chat if you're okay with that, that N is a vector of column names. It's 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 4 more. Come on, 4 more. Come on, Valentini, you with us? I got 20 people. I should get 4 more. 1, 3 more, 2. That's okay. Come on, 2 more, 3, 1 more. Don't be shy. I might give an extra point on the final exam if you say yes. Wow. There we go. Okay. But I'm not. So. All right. So yes, twice. Okay. Very good. All right. So here's what this is. What we're doing here, I'm going to focus on this piece of code here. So I'm going to copy this just so that you can see. If you look at this, not n percent in class, what this is doing is this is trying to determine whether in this vector, okay, in this vector, is there the word class? So watch this. If I just run this piece by itself, n percent in class, it is looking to see if the word class is in that vector. And remember, this is my list of columns. Look at the first one. The first one is called class, so it returned a true. All the rest are false. So what we're doing is, I basically want all of the column names that are false. So if I use this exclamation point, this is the opposite. So if I put the exclamation point in front, and I'll put parentheses here to make it a little bit more clear, it inverts the entire list. Now the ones that are true are the columns that I want. So the inner piece of this bracket is going to show me the column names where that result or that operation is true. So let me run this, and you will see that it has now given me all the column names except the classification column that is going to be my output. Does that make sense? That it now will give me only the names that I want. Please just put yes in the chat window. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. Awesome. 13 and 14. Excellent. All right. So now what I'm going to do is, if you're comfortable with that, now I'm going to basically take this paste command. What paste does is it takes anything in here, okay, all of the individual strings, because that's what it's a vector of character strings, which is all my column names, and it puts them together. What it does is when it puts them together, it says, put between them this plus. So when you run this, you get something that looks like this. You get a string that basically looks like alcohol plus malic acid plus et cetera, et cetera, et cetera. Does that make sense? This is the right side of the formula. So please write yes in the chat if you're okay with that. 2, 3, 4, 5, 6, 7, 8. Yes, yes. 9, 10. Good. Okay, we got enough. Got a quorum. So now what happens is, now that I know that this paste here creates pretty much what I want. I'm sorry, that's this one. The only thing that I want to do is I want to put in front of it another string that is class with the tilde, so that when I run this inner piece here, should be up to here. Okay, you see how I'm basically pasting again? I'm pasting this thing in the front, which is the class tilde, that when you run that, you end up with your full formula. Does that make sense as well? Can you please write yes if you're okay with that? One. Katie, you seem to be always first. Keep going, need a few more. Cool, awesome. All right, so now what happens is all I need to do is convert this string into a formula. And that's what this does. It goes as formula. So it's basically takes that full string and turns it into a formula that I can use here with FRM. So I'm going to comment these lines of code out here. I'm going to run this. And now my formula, this FRM, is ready for me to use as a regular formula in the neural network. This is something that you'll want to do when you have the handwriting recognition, because it is 768 variables, okay? But it's the same process. You basically figure out how to pull out your classification variable, and then basically you can use this, and you have your item in front, which is the classification variable. Create the string and create it as a formula. If you need help with that when you're running it, I'll give you a hand. All right, so now the neural network is the function that we're going to run. I have my formula. I pass in the normalized data set. I pass in the number of layers, the layers, which is 2 layers. The first one is 5, the second one is 2. And then linear output is equal to false. If I'm predicting a continuous variable, so if you remember last week we spoke about predicting an actual number, I would put here linear.output equals true. But since I'm doing a classification, the linear output is false. It's a classification. So we run this. And now what we're going to do is, don't worry about any warnings that you get. Closing unused connection. Oh, that's something different. We're going to run the plot. And you can't see the plot, so let me show you the plot. Because it opened up in another screen. And there's the plot. So here's my 5 variables. My 5 inputs in my 5 nodes in the first hidden layer. These are the 2 nodes in the second input layer, and it will return out a class. All of these numbers here are the numbers that are part of that weighted formula. These blue ones, if you remember last week, I talked about the W0, right? That's the like an initial weight, like a beta weight. That's what these are. They go to each formula, and it's actually determined that these are the best numbers to get you the classification. Okay. Going back to R really quick, does anybody have any questions on that? Or are we good to move on? Can you put in yes? Three, 4, 5, 6, 7, 8, 9.
Professor, I have a question.
Go for it.
The outcome would just be one single value, or is it like
Yes.
a range?
Well, it's okay. So it's going to produce a single value between 0 and 1. Everything in neural networks is 0 to 1. Does that make sense?
What does that tell us?
So it's actually going to tell us the likelihood, whether it's closer to 0 or 1. I'll get to that in 1 second, okay?
Okay.
For the output. I just want to make sure that you follow this so far, that we produced our neural net formula.
Yes, got it.
Okay. I think everybody else.
Professor,
Yep, go ahead.
for that formula, n equals neural net, the last one, output equals f. What
Yep.
does that mean? That
False.
output equals f?
Linear.output false means that it's going to produce a classification, not a continuous number. In other words, because what it's trying to do is the classification is a 1, 2, or 3. So you're telling it that it's going to be 1, 2, or 3. And that's what it's basing it on.
Oh, okay.
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 Any other questions? Okay. All right, so if I print NN, you'll see that I get all of these weighted coefficients, everything from that chart. You won't need this. You don't even have anything to do on your homework with this, but it's a lot of numbers, okay? What we really want to do is we want to do the prediction. So let's move to the next piece. Now, the prediction is really going to be the result. And this is what you were talking about, Valentina, is like, what is the result going to be like? So let me show you what that's going to be. Because once I have the formula, I need to actually do the prediction. Stop share, share. Where's that PowerPoint? Here it is.
Sorry, one thing.
Go ahead.
So the numbers that we just got would be like, I'm trying to kind of relate it to like what I already know. So let's
Yep.
say like the loadings from PCA, like
Yeah, they would
is
be
that
like,
kind of like
yep,
what we're getting?
kind
And
of,
then we're just doing a multiplication with the original data
kind of.
to
That's
get the
correct.
prediction.
Yeah, I would treat them more instead of loadings. I would treat them more
Mhm.
like regression coefficients.
Okay.
Okay.
Yeah.
But the difference is that you really can't interpret these. Okay.
Okay.
In the beta
Okay.
coefficients of your regression, you could interpret them, right?
Okay. But this will be the coefficients for the prediction that we're going to do.
Those are the coefficients for the various input nodes and all of the formulas.
Okay.
That's correct.
Got it. Thank you.
Remember, in the first layer that we have 5 input nodes, that means you're going to have 5 equations total for the first layer, because each node has its own equation that it's working with. Does that make sense?
Yes. Got it.
Okay. So that's why it gets a lot, those are a lot of equations, and that's why they're really not easily interpretable. They're not really interpretable, in my opinion. All right, so that's what the chart looks like. That's what we just drew. So as you can see, we've got a bunch of input nodes. Each input goes into this node, goes into this node, goes into this node, goes into this node, goes into this node. The outputs of the first layer go into as inputs into the second layer. The outputs of the second layer go into the inputs of this third layer, which really is the output layer, which is now going to give me a value between 0 and 1. So if you get a row of information with all of these things, we can plug them into the neural network, and it will give us a number between 0 and 1. That number between 0 and 1 will now represent the classification itself. So, as I said, it basically produces a number between 0 and 1. That's what this compute function does. Since we have 3 classes, what we're going to do is we're going to set an arbitrary cutoff. We're going to basically say that if you're between 0 and 0.33, then your class is 1. If you're between 0.33 and 0.66, you're going to be a class 2. Now, the problem we've got here is that 3, 4 to 6, 6. So the way you would really read this, if it's less than 0.33, it's a 1. If it's less than 0.66, it would be a 2. Remember that the 0.33 is already done, so you wouldn't have any left over. So anything that's 0.66 and greater will be classified as a 3. So let's see how that works. Here, I've got this NN. Here's my neural net. That's the formula we passed in. It gave us our resulting computational object. I have that. I'm going to use this covariate equals, which is basically what I'm passing in for the data. So the data that I'm passing in is the y normalized. Anybody tell me what the -1 is? What this y norm -1? Oh, you can't see R. Andy, if you can't see R, just you can yell that. You don't have, because sometimes it's hard for me to see the chat. Sorry. Okay. So let me do that again. So I've got this compute function which takes in the neural network object that we had. I'm going to pass in the next parameter, which is called the covariate. This is the actual data. I'm going to, in that covariate parameter, I'm going to pass in a y norm -1. What is y norm with a comma -1? What am I doing here?
You're not taking the first column.
Right. And why would I not want to take the first column? What's in my first column in this data set?
That's the class column.
That's the class column. And so I want to use the other data to do my prediction. I don't want the class column in here. I only want the other data. Does that make sense?
Yeah.
So now I run that compute function, and I could have done it this way, which may make more sense if you like. CMP equals, and I'll copy this compute like this. That would give me a result, but it's a very large object. And the actual answer for my prediction is in this CMP now net result. I actually combine them here on the one line. It takes the object itself, and the only thing I'm really interested in is what the result is. When we run this, I'm putting it back into the Y norm as a column called predict. So when we run this, I'm going to look at Y norm. It should be this one. There we go. There's my Y norm. Here's my original class. And here is my predictions. And if we look carefully, they are all between 0 and 1. Does that make sense? Go in the chat. Are we okay? Just say yes if I can move on. Excellent. All right, cool. So now that I had that, and that's my result, I really would like to make it a little bit cleaner, and this is what I showed you in that PowerPoint. So I've got this function here called if-else, okay? We read it this way. If-else, and here's my condition. If the predict column of the Y norm data set is less than 0.33, then this will return a 1. And we're going to put that into this predict class column of the Y norm data set. So if Y norm predict is less than 0.33, we put a 1. If it's not less than 0.33, I will run what is here in the third parameter. But it happens to be another if else. And I do it again. If else the predict column is less than 0.66, it will return a 2. Otherwise, it returns a 3 and we're done. And it's easy to do this when you have like 3 classifications. It's not easy if you have 7 or 8. You won't write it this way. You'll write it as a probably as a loop or nested ifs a little bit differently. But you won't have that for this class. So does that make sense that when we run this at the end of the day here, if I run this, you'll look at Y norm. There's a new column at the end called predict class, and it has taken this predict and now created it either as a 1, 2, or 3. Let me know if that makes sense. Can we write yes in the chat window? 2, 3, 4, 5, 6, 7, 8, 9. Come on, give me 5 more. 1, 2, 3 more.
Professor, I had a question.
Go ahead.
When it's, how do you know that 0.33 is correlated to the 1 value?
Because yeah, that's so.
Originally, how do you like?
Because they're ordinal.
They're ordinal.
Because
Okay.
if the quality is ordinal, I can do that because I know the 1s will be lower than the 2s or lower than the 3s, and that's how it scales. If it wasn't ordinal, you could not do that.
Okay.
And I'll show you that in a second. Okay?
Yep.
Cool. All right. So now what I'm going to do is I'm going to look and see how well we did. So I'm going to add another column at the end called class original, and I'm going to put that class variable in. I'm only just creating another column so I can easily see this. You don't have to do this. But when I run this and you look at your Y norm, at the very end, you see there that I have the original class. And it looks pretty darn good. See that? All 2s. My predict was 2. The original was 2. My prediction was 3. The original was 3. So that's really good. So when we're doing our measures of accuracy, I'm looking for the hit rate. So I'll compute something. How many times did we predict it correct, and how many times was it wrong? So here, what I'm doing is I'm basically creating a new column called predict win. Was the class equivalent to the original? So when you run this, you'll see at the end, I get a 1s if it was true and 0s if it was false. So when we look at the code here, you can see that I get the ones and the zeros. And if I sum that up, if you sum up the wine, norm, $, predict win, they were all right. I got 178 of them. If it was wrong, it would have been a 0. Does that make sense? I'm going to stop right there. Can you write yes if it's good? 1, 2. Okay. Does anybody have any questions before I move on to multi-node? Multi-node outputs is what I meant. Okay. All right, so moving right along. So now, let's go back into, oh, this is gonna be a problem, I just realized. I might have a problem with this on YouTube, by the way. I just realized. Hold on one second. You know, when I try and put it up on YouTube, I'll see. But the TV was in the background, and I completely forgot. And sometimes it gives you a copyright strike because it notices the TV's in the background. All right, so we did that. We did our numbers actually already. Now what we're going to do is we're going to do multiple classes. So let's go back to, I don't think I did it here. Yeah, okay. So now what we're going to do is we're going to do multiple classes. So I'm going to do this from R. So here, what we got here is I need to create, so we say, you know what, I actually want to compute 3 output nodes. So responding, one for one class, one for another class, one for the other class. So I have to create dummy variables in order to do that. So what we're going to do is I'm going to create 3 new variables, class 1, class 2, class 3. And I'm going to look at the class.
Share your R.
Oh, thank you. Thank you. Stop share. Better? I'm assuming it's better. Okay, good. All right, so here what I'm going to do is I need to create the 3 new variables. I'm going to create a class 1, a class 2, and a class 3. So now what happens is that I'm going to look at the original class, and if it's a 1, this would return a true or false. So I can do as numeric, and it will convert trues and falses to 1s and 0s. Okay, and so that's what this does. These 3 lines of code will basically look at the class, and if it's a 1, it will put a 1 in class 1. If it's a 2, it'll put a 1 in class 2. And if it's a 3, it will put a 1 in class 3 and 0s otherwise. So when we run this, oops.
So this is
Go ahead.
this is what we would have to do if the class wasn't ordinal.
That's correct.
Okay.
Okay. Now, even if it's ordinal, right? If you have too many levels, like in your handwriting recognition, you'll have like 10 possibilities, 0 through 9. Now what happens is that if you had a single output node, you'd have to be doing levels of between 0 and 0.1, 0.11 and 0.2, 0.21 and 0.3, right? And so forth. That's not a lot of space to make for, you know, for errors. Does that make sense?
Yeah. Mm-hmm.
So that's one of the reasons why we'd want to create these multi-nodes, these multiple output nodes.
Okay.
So when I run this and I look at wine multi, which I think is this one, there's my class 1, my class 2, and my class 3. Okay? All right, so now what we're going to do is we're going to basically do this C-bind again. What I'm doing here is I'm applying to the this new multi data set across columns, min, max, normal. And what I'm doing is I'm just going to bind back the first column. So I'm basically leaving the first column alone is what I'm doing. We run this. And I'm doing that for a reason because I think it is, Wine multi-norm. I gotta see which one that is. Why isn't it running? Taking a while to run. What's going on? I'm gonna pause the recording while I figure that out. Oh, there we go. All right, so that's correct. But let's rerun this. Yeah, did it. I must be looking at the wrong one. All right. So after I run this and I have the wine multi-norm, okay, this is kind of like duplicate code. I don't really need this. I added the column back in because what I was going to do was keep it, but this then removed it. So you don't really need this. Not really sure why I did that, to be honest with you. So I'll have to fix that. All right. So now if I look at wine multi-norm, which is this data set, where's my columns? You'll see here I've got all of these items. Down at the bottom, I should have added 3 additional nodes, class 1, class 2, class 3, which is fine. That should be, oh yes, these are between zeros and ones. So if you look, I got confused a little bit here. If you look, this number is already between 0 and 1. So if it was a 1, it's going to be a 1. If it's a 0, it's going to be a 0, which is what you would expect. Unlike the previous classification variable, where it was actually a number between 0 and 1 where you had decimals because you had a classification of a 1, a classification of a 2, and a classification of a 3 in the same variable. So once we've got that, I'm only going to change, I'm going to run that same formula function. I'm sorry, I got to do the neuron estimate first. I have my same, roughly the same inputs. My outputs have now changed from 1 to 3, because now I've got 3 outputs. I run the same thing. My neuron estimate, let's see what it comes up to. 6. Why? Because I've added another input. I'm sorry, I've changed the output, so I don't need as many neurons in between to calculate that or to compute it. I run the same function that I did before, only this time, instead of just class in the front, I'm going to do class 1 plus class 2 plus class 3. This is how I represent multi-output nodes in the neural network. Does that make sense so far for this, for the multi-output nodes? Just write yes in the chat if you're okay so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Come on, give me 3 more. 11. 2 more. 12.
Wait, so should the n equals names? Why didn't we do n equals col names of wine multi-norm?
So when you run this, oops, sorry. Let me just double check. Maybe it's a typo. Yeah, it should be call names. Now you get it. Thank you. All right, so we've got that. I've got my output here for each one of these, which we're good with. The only difference is I'm now comparing, I'm going to exclude class 1, class 2, and class 3 as a vector. Remember before, I only looked for one thing. I only looked for the class variable, but you can use that same method to look for multiple names and exclude them from the list, which is what I'm doing here. This form function, when I'm done, I can basically, I clicked it too fast, I'm sorry, form. There's my formula, class 1, class 2, class 3. Here's the alcohol, malic acid, ash, etc., etc. Now what we're going to do is we're going to run it again here in the neural net. So I have my form. I have the wine multi-norm as the data. I'm going to use the same hidden 5-2. Now I got a problem because my neuron estimate said before that I should only really have 6. But I'm giving you 5 and 2. So there is nothing that says I have to use that 6. I could add a little bit. I could take away a little bit if I get better accuracy. But remember, if you're doing that, you may be overfitting based on what's going on. What I'm doing here is I'm trying to show you what the result is between using the same hidden nodes. And then we'll change it for one and we'll see what happens. So I'll run this. I get my plot, which will hopefully generate. And you can see the plot here. And this is now my new plot. Those are my inputs. And then I have 3 outputs over here. Does that make sense? What do you notice here? Anybody? In the chat. Makes sense, Andy? Does anybody notice anything peculiar here? 3 more lines, that's correct, but what else? Your tree structure may be a little bit of a problem, because what you're going to notice here is that I've got 2 nodes now trying to predict the 3 nodes, 1, 2, and 3. Now again, it may or may not be an issue, okay? And some applications don't have a problem with this. You'd like to keep something a little bit more simple. I like the hierarchical tree structure myself. I think it's a little bit more understandable or intuitive. But if I have if I have 3 output nodes and I only have 6 hidden nodes, the question is going to be, how are you going to structure that? I may have to do 6 hidden nodes in one layer to get to my 3 output nodes in order to get the tree structure. The issue really is, though, that again, you have a lot of latitude to put these nodes in whatever order you want, as long as you can ultimately get the right result. What I'm giving you are the rules of thumb on how to do it. So going back to R, we're going to basically do the exact same thing. Can you see the R?
Yes.
Okay. All right. So we ran our neural net. I plotted it. Again, plotted it. Now, these are some of the things that are available inside of the neural net, which again, we're not going to use, but you have the actual weights associated. We said you have all those numbers. I can have a resulting matrix if I want, which is basically like the inner workings of the neural network. I don't need the names of the one multi-norm, but I'm going to now do my computation. I'm excluding 14, 15, and 16 because that is where my class 1, class 2, class 3 variables were. So I'm doing the exact same thing that I did before. I'm going to run this. I will now bind it back. I'll take that prediction, which is this new thing. I will bind it to my 14 through 16 that I had before. The reason is because this is only going to give me my predictions, which is the 1, 2, and the 3. See that here? 1, 2, and 3. This is your class 1, class 2, class 3. When I bind it back and I combine them, I'll show you what that looks like now. I've added the original values. This is the original values, the original predictions, 1, 2, and 3. If you notice the numbers here, okay, in the first column, it's a 0.99. And look what the class came out to, 1. The others were very low. And those were represented as 0. So what you would want to do is you would want to basically write a small if-else here that would basically say whether or not it was correct or not. If the prediction class is going to be, you could say the larger of the 3, or the one that's greater than 0.5. And you'll see that that seems to hold across all of them. Here's your 0.99s. They're all 1s. Then it will flip somewhere. Here, it flips now to the middle. They're all 1s. And then it will flip again here, where the third column is now all 1s, and it's predicting your class structure the same way. Does that make sense? Any questions so far? Let me know if we're good. Just type yes. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2 more. Come on, 2 more. 12, 13. Thank you. 14. Awesome. Okay. So let's see what happens. I'm just curious. Let's have some fun. I'm going to go back to the original one. And I'm going to change it from 5.2 to 3. I got to rerun the class. Class 1 not found. I got to rerun this because I think I screwed up the data set. So let's see. Fly 1, neuron estimate. Boom, boom, boom. That should be good. Perfect. All right. So let's see how well we did. I'm not going to worry about plotting it. I only want to compute and do my prediction. I'll do the same thing that we did before. Predict wins. Now let's see what it looks like. So I go to Y norm. Here are my predictions. So the prediction class, the ones basically mean we won. And it still looks like it predicted everything perfectly. So even with a smaller number of nodes, here, 3 nodes, it still got it right. Does everybody see that? Is there anybody who doesn't see that? The problem is that this is such a regular kind of data set, and it's very small. It's easy for the neural network to win. Now, ideally, what you're going to do is you're going to take a training set of 80% and predict the 20% using the same thing. The only difference will be your covariate when you do the prediction. You're just going to change, you're going to run it for the training set, and then you run it for the test set. It's the same function. Okay? Just like the predict was, you're just using it for compute. Let's change the, well, change the other one's going to give you the same result. So, all right. So now, if we're okay with that, I'll move on without objection, unless there is. Let me stop share. We're going to go back to the PowerPoint. Right here. Now, what we can do is we can actually use neural networks as a regression to predict a continuous variable. So in this case, we have a totally different data set. I've got this air quality data set. We're going to make sure that there's no missing cases. So we're going to see if there's complete cases. I'm going to do this again a little differently. We're going to compute the number of neurons that we need, which in this case, we'll probably end up with 2 hidden layers and 8 neurons, as you'll see in a minute. Our formula is written the same way with our dependent variable out here. It'll be 1, but we're going to change the linear output to true because we're going to indicate to the neural network that it's going to be a true value. Okay, so let's go back to R. I don't know why R came out down here. All right, form numbers, errors. Okay. Oh, I don't have, oh, maybe I do, hold on. Okay, the air quality data set should be built in, so you should have this, okay? It's part of the base in R, so that's why I didn't load up a data set. So what it looks like is ozone and some other features like solar R, wind, temp, month, and day. So I'm going to run this function again to determine if there are any NAs. This is what we did before. I apply on the air quality, each column, I want to get all the sum or the count of the NAs. And as you can see, we have 37 NAs for the ozone layer. So we're going to have to remove those, and we've got 7 for here. So in this case, I'm going to create a new air quality 2 data set, which is only going to take the complete cases. So this is similar to what we had done towards the beginning of class when we ran complete cases. So we'll run this. Now my air quality 2 will basically have no NAs, but I've lost a couple of variables. Someone have a question? Uh-oh, I heard heavy breathing. Anybody got a question?
没有回定补功能的。
好了，上去了。
其实是有的，我找找。
Okay. All right. So now that I've got that, I'm going to normalize the data set. It is now normalized. I'll run this so that you can see that. Everything is normalized, including my ozone, which is fine. I'm going to compute the inputs and the outputs and compute my neuron estimate. So the total number of neurons that I need for this data set is approximately 8. I'll get my column names, and I will do the same formula here to basically create the formula for me. I did that before. And so now I'm going to run the neural net with that formula. This is the formula that I created, which is perfect. I'm going to basically use that formula. I'm going to use the data set, which is the normalized data set. Now I've written 5.2. I probably should write 5.3 because it said it required 8. But this time I'm going to do linear output is equal to true. So I'll run this, and we'll plot it.
I forgot. What does a true and false mean again?
True would mean we're doing a regression for a continuous output. False means a classification. We're trying to predict a class, a 1 or a 0 of something.
Got it.
Okay. So here's now my formula, my regression, the neural network. I have my inputs. I've got 2 layers, one of 5, one of 3, which is okay. I probably would prefer 4 and 2 in this case, maybe, to create a smaller tree, but this is perfectly fine. You'll notice at the bottom, it gives me a 36% error, and it took 369 tries to get this model. It says this is the best model I can get. So we go back to our code. Okay, hopefully you can see that. And now I'm going to compute the errors. So computing the errors again is going to be our measures of accuracy. I'm only going to compute 1, but I'm going to basically bind the ozone along with, now I've combined everything here. I created a data frame with this compute and then everything minus the first column and the results. Remember, this will give me the predictions as they stand. That's what the predictions are. So I'm going to compute this, bind them to the air quality ozone, and now I'm going to get an error rate, which is basically this minus this. That's all I'm looking for. Rounded to 3 decimal places. I will take the mean absolute error, and I get a mean absolute error of 0.06 from the actual values. So I can now use this if I want, right? So that's a 6% error rate when I'm using it to predict the actual data. I didn't compute the other measures like the absolute percent error, the absolute or the percent error. I only computed the mean absolute error here. You should always compute the all 4. The mean error, the mean absolute error, the mean percent error, the mean absolute percent error. But you can see that it pretty much gave me a reasonable number. You can invert this by using that formula. Instead of giving you a number between 0 and 1 for the actual predictions, which is what this is here, I could invert this using that formula from one of the first slides in the neural network component, where we took each observation, subtracted it from the mean, and then divided it by the range. Okay, we did the exact opposite. We have to do the exact opposite, which I showed you the last. Oop, I ran too many. 1, 2, 1. Yeah, just 1. Sorry. This one. Close. I don't need the parentheses, that's why. There we go. So this is the normalized prediction. So we can unnormalize it by using that formula from the previous lecture. Okay, does anybody have any questions on that from the R code? If you're good, just reply yes in the group chat.
I have a question. If I wanted to change that 5 and 3 to like 2 and 6, would I give a different number for the absolute error?
So the answer is that it would give you different computational values, but you'd have to test it to see how good it did. You follow?
Yes.
Okay. It's the only way to tell us. You'd have to literally try the 2.
Mm-hmm. Okay.
Okay. All right. Okay, so let me pause share really quick. I'm going to go back to, I think that's it on the PowerPoint, because we did this over too. But I do want to go over one more thing. Where did it go? There it is. Data mining. And homework. Science. Assignment 3. I'm going to